now it's time to introduce the next speaker, Professor R Al Raoush, who is based at Qatar University. Professor Al Raoush is a professor of environmental engineering at the Department of Civil and Architectural Engineering at Qatar University. His research interests include the fate and transport of contaminants in subsurface systems, environmental fluid dynamics, multi-phase flow through porous media, and environmental soil physics. Professor Al Raoush secured more than $3 million in research funding from agencies such as Qatar National Research Fund and the US National Science Foundation. He has published more than 50 peer-reviewed papers in top journals in his field. He's a frequent reviewer for many international journals in the area of environmental engineering, water resources, geophysics, and geoenvironmental engineering. He was a visiting researcher at US national laboratories, including Argonne National Lab, the Pacific Northwest National Laboratory, and Los Alamos National Laboratory. And Professor Al Raoush will talk to us today about synchrotron microcomputed tomography for geoenvironmental applications. Professor Raoush, it's a pleasure to have you here with us. The floor is all yours. Professor Raoush, you are muted currently. Could you unmute yourself? And yes, let's begin from the... Okay. Yes, we can hear you now.
Okay, assalamu alaikum everyone, and thank you for the opportunity to talk about our research applications of computer tomography. We listened to excellent talks yesterday and today morning on the use of computer tomography and its advantages. So the focus of my talk is going to be on the applications of computer tomography for geoenvironmental engineering. So I will focus on the applications. I will talk about core scale experiments and image processing and analysis. So synchrotron computer tomography can be used to study a wide range of energy and environmental applications. So here are just examples of some of the investigations that we did in terms of environmental applications. We did experiments related to physical and hydraulic properties of granular material, groundwater artificial recharge and dewatering, fine migration in subsurface systems, and contamination with colloids and petroleum hydrocarbons. For energy applications, we did related work to enhance oil recovery, methane hydrates, microbial enhanced oil recovery, and this is just an image that represents a sample obtained from computed tomography. So you can see that we have three phases. We have the oil, solid, and the fine phase. So why microscale? Many environmental processes and phenomena take place at the microscale level or the pore scale level. Therefore, to better understand these at the larger scale or the macro scale, these processes or phenomena must be investigated at the pore scale. This figure here shows an illustration of how contaminants transport through porous media from underground tank towards a fresh groundwater aquifer. As you can see here, mass transport mechanisms of contaminants take place at the microscale level or the pore scale level. Therefore, there is a need to obtain non-destructive 3D images at the resolution of microns to observe and investigate microscale processes for different applications. So the overall experimental approach that we adopted here is we design and conduct microscale experiment based on the application of interest. We obtain non-destructive 3-dimensional high-resolution images of systems at different experimental conditions, and we develop and implement robust and efficient algorithms for image processing and quantification of the relevant pore scale processes from the large 3D images. So why synchrotron microcomputed tomography for our applications? Synchrotron microcomputed tomography is an imaging technique that provides non-destructive imaging, 3-dimensional high-resolution images on the order of microns, and most importantly, energy is tunable to obtain better contrasts between the different faces that we have in the images. So this figure here shows a top view that illustrates a typical tomography beamline. The sample is mounted here, and it passes, X-ray passes through and around the sample, and the sample rotates around vertical axis with a specific angular increment. Then the projection passes through the scintillator and then reflected by a mirror toward the CCD camera. This image here, it's part of our experiment that was conducted at the Advanced Photon Source at Argonne National Lab in the United States. What you see here, this is the image of the 6 giga electron volt storage ring. And these pictures here shows some of the experimental setups that we developed and used for 3-dimensional images for different applications. And I will talk about these shortly. While all the 3-dimensional images obtained, while all the images obtained from tomography are 3D, this image here shows 2-dimensional cross-section. It just shows different faces inside the column. This slide here shows the experimental setup that we use to conduct multi-phase flow experiments. In these experiments, CO2 was injected into saturated porous media and was imaged at different CO2 saturations. Monochromatic X-ray radiation was used to scan the specimen, and the injection of CO2 took place on the moving stage. As you can see here, the setup was equipped with top and bottom ports, which were linked to tubes that allowed fluid flow. The bottom port provided gas, while the top port was used to drain water in order to allow gas to invade the pore space. Vertical springs here were added to apply stress to the porous media. Image C here, the 3-dimensional image shows a 3-dimensional image of the interior of the object where CO2 is shown in blue and the sand is shown in gray. Here, to enhance the contrast of the faces of the image, what we did, we doped the water by adding 2% of potassium iodide to enhance the contrast of the faces. Then the sample was scanned at 2 different energies, below and above the iodide edge. You can see here the image size is about 2000 by 2000 by 1000 voxels, and it took about 15 minutes per scan to complete the experiment. And the resolution of the image that you see here, it's about 3.6 micron per voxel. This is the setup, the experimental setup that we used for hydrate formation and dissociation experiments. The setup was designed to control the pressure and temperature to simulate the formation and release of hydrate from deep reservoirs. Pink beam synchrotron tomography was used to obtain non-destructive 3D images. Pink beam uses a grazing incidence mirror and an X-ray absorbing foil instead of the monochromator to eliminate high and low energy photons, which gives a high flux of X-ray 3 order of magnitude higher than the monochromatic beam. This was necessary for our work because the X-ray needs to penetrate the thermal insulation that we have in our sample. and the high pressure cell that we used for this setup. The total time for this experiment was about 12 seconds, the scanning time, and the experiments were run for more than 4 hours for hydrate formation and another 4 hours for hydrate dissociation. This is another experimental setup, a series of experiments that we conducted related to multi-phase flow in porous media. The objective of these experiments was to investigate patterns of fluid entrapments and their correlation with the physical and chemical characteristics of the porous media. Here, the setup shows the experiment. I mean, the column that we use, or the cell that we use, the inside diameter of the column was about 6 millimeters, and the height of the column was about 8.5 centimeters. The column was connected to tubes and pumps that allows fluid injection into the cell, and different porous media or different sand was used to represent natural porous media systems. We used different fluids, including citral, water, to represent immiscible fluids in the experiments, and to investigate the impact of wettability of the entrapment patterns of the fluids. Fractionally wet systems were obtained by combining various mass fractions of untreated and treated sands. The experimental cell was packed with porous media at different initial conditions. One of the advantages of synchrotron tomography is that the energy can be tuned to enhance the contrast of the phases of the image for a better segmentation of the faces or the images. To utilize this advantage, fluids used in our experiments can be doped with certain chemicals, and then the systems are imaged at energies just below and just above the edge of certain elements. For instance, in our experiments, the oil was doped with iodobenzene and the water was doped with cesium chloride. And you can see in this system here, the system was imaged at 2 different energies just below and above the edge of iodide, which gives a good contrast of the oil phase in this image. Once we have 3-dimensional images obtained from computed tomography, image post-processing and segmentation are needed to convert grayscale images to binary images, so we can work with them and we do some quantification. So there are many segmentation algorithms available that can be used to achieve the segmentation step. Also, there are different filters that can be used to enhance the quality of the images. So for instance, in this case, we use anisotropic diffusion and median filters to enhance edges and boundaries of the faces before the segmentation step. As I mentioned, there are so many segmentation algorithms available, and this is very critical for our analysis. So here what I show is just an example of image segmentation technique, which is indicator creaking approach. In this method, basically faces are identified based on the histogram of the intensity of the values in the image. You can see here, this is a grayscale image obtained from computed tomography that has 3 phases: sand, water, and oil. And this plot here shows the histogram, the corresponding intensity histogram of the image. The segmentation is done based on the 2-point correlation function. So for example, values below T1 are assigned to one phase, between T2 and T3 are assigned to another phase, and values above T4 are assigned to a 3rd phase. And the uncertainty here is between T1 and T2 and T3 and T4. In this case, we use 2-point probability correlation function to identify the phase. In this slide here, I show the outcome of an algorithms that we developed and used to identify individual particles of systems of granule material using 3-dimensional images obtained from computed tomography. This enables us to obtain complete characterizations of system at the particle level. This is very essential, very critical in many engineering applications such as force transmission, failure mode, and so on. What you see here, this is a 3-dimensional output of the code that we developed and used for identification of individual particles from 3-dimensional images. Different systems are used here. This enables us to obtain complete 3-dimensional characterization of the systems at the particle level, which is very critical to engineering and environmental applications. This is another application or another series of experiments that we did we conducted experiments to investigate the stress-strain correlation and the impact on the particle displacement and evolution of the pore space. These are three-dimensional images obtained from computer tomography. These are real-time experiments, and we look at the increment of stress-strain at different times and different stress increments. And this gives us critical information for geotechnical engineering design and applications. These are some of the measurements that we can obtain from three-dimensional imaging in non-destructive way. This is extremely important for our applications. So for example, figure 1 here shows the distribution of grain diameters in a sediment sample. And figure B and C shows the distribution of important shape indices, namely the sphericity index and the roundness index. And you can see here, these are the three-dimensional images of these distributions. And everything here is done non-destructively, which is, a critical factor in our research. This is another series of experiments or another environmental application where we use synchrotron microtomography. Here we looked at the distribution of trapped fluid in different geometries of the porous media. You can see here, let's see if I can see my pointer. Yeah, so here we looked at the distribution of trapped fluid in different geometries of the porous media. From 3D images, we can obtain complete and accurate characterization of the trapped fluid as a function of the pore space. The inside diameter of this column is about 1 centimeter, and this data is very useful application to enhanced oil recovery, remediation of contaminated groundwater, and so on. You can see that this gray here is the solid, and this white here is the oil phase. This is another three-dimensional image. It's an outcome of a computer tomography experiment that we conducted. We looked at the trapped blobs in the pore space. The size of the sample is 1 millimeter by 1 millimeter by 1 millimeter here. This image shows the distribution of individual blobs. And you can see these are identification of discrete or individual blobs. From this system, we can obtain parameters such as length, volumes, directions, and these can be used as input to models that predict processes such as mass transfer. These are three-dimensional images obtained from computer tomography experiments. We looked here at the impact of wettability of porous media on the characteristics of the trapped blob in the pore space. Again, these are non-destructive images. The size of the sample was 1 millimeter cube. These images show the identification of individual blob and the impact of wettability on the distribution of these residual blobs. This is another experiment where we use computer tomography. We looked at the dynamics of hydrate formation and dissociation in porous media. We used xenon gas and was injected into a full saturated sediment at a temperature of 10 degrees centigrade and a pressure of 1.9 megapascal. These are cross sections from 3D images where the inside diameter, again here, 1 centimeter. These images shows how we can capture the development of hydrate as a function of time. You can see that this gray scale here is the porous media or the sand phase, and the white here, it's the hydrate formation as a function of time. This video here shows a sequence of raw tomography images captured continuously at a time step of 45 seconds. This shows the hydrate dissociation at the pore scale and how parameters such as volume, interfacial area develop as a function of time and saturation. Understanding and quantifying these parameters at the pore scale, it's a key factor to develop reservoir scale or macro scale models for natural gas production from methane hydrate. These segmented images shows the outcome of the hydrate formation experiments. You can see from these tomography images, three-dimensional images, we can identify 3 types of habitat formation. Namely, we have surface coating here, we have cementing here, and we have pore filling here. Such observation in non-destructive fashion is very important, not only to predict gas production from hydrate methane sediments, but also it's important to evaluate the safety and the structural stability of hydrate reservoirs. This is another study where we use synchrotron microtomography to investigate the impact of pressure on the gas conductivity in sandy sediments. So for the same geometry of the porous media, for the same topology and geometry, you can see that here we can quantify two types of flow regimes at low pressure here. You can see that gas phase is highly connected. However, at this low pressure or at this high pressure here, you can see that the gas phase gets disconnected to individual or multiple gas blobs. This is another experiment. We use synchrotron computed tomography to investigate the impact of the type and the percentage of clay on gas flow or in unconsolidated porous media system. As can be seen here, we have three types of flow patterns. In figure A, we can see that at low content of clay, the gas is connected and flowing in a capillary fingering behavior through the sediments, this one here. And in figure B here, we can see that at high concentration of colonite, you can see that the pore space is clogged, which in turn causes microfractures. In figure C here, you can see that at high concentration of moronite, this is another type of clay, the gas is disconnected, which in turn increases the residual gas phase saturation. This is zoom for the type of behavior that we see if we inject clay in our system. You can see that gives us information about the clogging behavior. You can see on this image here, the clusters of clay or colonites are observed to be attached on the sand-water interface. So we can identify what type of interface we have here. And actually this causes clogging of small throats, which in turn gives gas-induced microfracture. However, on this image here, moronite is observed to be attached at the gas-water interface, and that causes disconnected gas phase and okay. This image here shows the impact of the type of clay on the flow of gas in porous media system. We can see here in this image, colonite causes gas flow is a continuous phase. This one, this red one here. However, in this case here, you can see that another type of flow, which is moronite, causes gas to flow as a disconnected phase, which in turn increases the number of trapped residual gas phase in the system. You can see that here, every color represents a different gas phase. Pore scale modeling is a powerful technique, powerful simulation technique that allows understanding of single and multi-phase processes at the pore scale. So three-dimensional data from microtomography is essential to validate predictive pore scale models. So two methods are available here, the lattice-Boltzmann modeling technique and the pore network modeling technique. Lattice-Boltzmann method utilizes or considers the full complex geometry of the porous media or the pore space, which gives accurate predictions. However, it's computationally expensive. On the other hand, the pore network modeling here uses a simplified geometry of the pore space, and it gives reasonable prediction of the pore scale processes and phenomena. Here you see the simplification of the complex pore geometry to the pore network structure, which is the base for pore network modeling. This pore network structure is used for pore network modeling based on the physics of the relevant problem of interest. You can see that this is a simplification of the void space. In other words, the pore bodies connected to pore throats. There are so many algorithms we use or actually available to obtain the distribution of pore bodies and pore throats. And you can see that in this image here, these are the pore bodies and these cylinders are the pore throats. So we can follow the physics of the fluid dynamics in a sample like this one here, so we can build predictive models. This slide here shows an example of the outcome of pore network of a sample of unconsolidated porous media. So we see here pore size distribution. You can see here throat size distribution. You can see here coordination number, which is the number of throats connected to a pore. And what you see here is the throat length distribution. And these distributions, as I mentioned, they are used as input for pore network modeling approaches. This is an actual microtomography image from an experiment that we did. You can see that this one here, this is the gas phase through the porous media, and this is actually the pore network. Is it this way? This way? Yeah. Here we use computed tomography to obtain three-dimensional, non-destructive measurements of tortuosity of soils. Tortuosity is an important pore scale parameter that describes the flow paths in a porous media. So you can see here, these are the flow paths. This is two-dimensional cross-section out of this three-dimensional image. You can see that these are the paths of if the flow comes in this direction towards this direction here. And this one here, these are all possible paths of a given fluid if it's injected at this point here to this point here. This is actual computed tomography image, and this is one of the algorithms that we developed to obtain tortuosity. These are some just images of pore network structures. And here I show the analysis of representative elementary volume analysis for porosity. The REV is the smallest volume of a given sample where the property of interest is constant regardless of the spatial location of the size of the sample. In other words, it is the minimum size needed for a sample to be representative in terms of a given parameter. So using non-destructive three-dimensional images obtained from computed tomography, we can determine the REV of a given sample. Here I show the REV determination. Basically what we look at expanding volumes, and we look at the parameter of interest. In this case, it's porosity. So whenever the property of interest is constant, so we consider this an REV minimum, which is the minimum representative volume for upscaling. Here I show the representative elementary volume for different soil samples. And as I mentioned, the finding or determining REV is a link between the pore scale and the macro scale simulations for any geo-environmental applications. I would like to thank Qatar University, Qatar National Research Fund, and Argonne National Lab, my collaborators at University of Tennessee, Chongbuk National University, South Korea. And I would like to thank my colleagues, Engineer Jamal, Professor Khalid, and Professor Jung Wong, and Dr. Zahir Jarrah. Thank you so much, guys, and please let me know if you have any questions. Thank you.
Thank you very much indeed for most interesting talk. We are very pleased to have you with us. And at this point, I would like to ask the audience if there are any questions for Professor Al Raoush following his talk. Are there any questions, any discussion points, queries that you would like to?
Actually, I would have one or two questions, if I can.
Yes, please. Do go ahead, Gianluca.
First of all, thank you very much. The talk was very interesting. I think it's very promising for us to see already such a broad and diverse expertise in computed tomography. So I wanted to know, you showed several time-resolved studies, which of course is very interesting. For many of them, I have the feeling that the time resolution and the speed of the experiment was something that we could do at Beats. You showed one example where the different time steps were separated by minutes. So you were tracking a process over 15 to 20 minutes. I think it was in gas formation. You also showed an example of strain evolution in a granular mix. What was the speed of that experiment? Was it also like minutes, or was it faster than that?
Professor Raoush. I think you are muted. We can't hear you.
Okay, no, it's good. Can you hear me now?
Yes.
Yeah, sorry, I'm using the computer of my student here, so I just moved here. Anyway, thank you. This is a very good question. So for the hydrate-bearing sediment, we are looking at the development of the hydrate, and the scanning time for the experiment was 12 seconds, and the running time was 4 hours for development of the gas and 4 hours for the dissociation. So it's about 8 hours of the experiment. But the time of the scan is about 12 seconds.
And what about the mechanical test with the granular mix?
Jamal, I'm sorry, question again?
What about the mechanical test? You showed a mechanical test of a sample with a mix, a granular mix, where you were tracking the strains.
Okay, so that was, I think it was about 25 minutes. Yeah, it was 25 minutes. Yeah, the scanning time. Because we want to reach to a quasi-state equilibrium.
Mm-hmm. Maybe one more question, if I may. You also showed experiments done with K-edges, so energy resolved and probably image subtraction. Those were done on a beamline with a double crystal monochromator, I imagine.
Yes, yes.
Okay.
What happened is our interest here, we just want to make sure that the doping percentage does not change the physical and chemical characteristics of the material. So we did some preliminary investigations. So we found that 2%, 2 to 3% is appropriate for our fluids. That does not change, parameters such as density, viscosity, surface tension, and so on, because these are very critical to our experiments. So. And we use different materials such as cesium chloride and iodobenzene and so on.
Okay, thanks a lot.
Thank you.